In our last video, we saw how to prepare carboxylic acids using a variety of ways. Today, what I want to do is look at the reactions of carboxylic acids. And there's a little bit of review that I wanted to go over because we have seen some reactivity of carboxylic acids before. And in particular, I wanted to focus on this reaction where we go from a carboxylic acid all the way to a primary alcohol. In order to accomplish this reaction, we need a really strong reducing agent. So in this case, what we're going to use is LaH, or lithium aluminum hydride, and we're going to use excess of that. And in step 2, we need to ensure that everything's protonated, so we're just going to do an aqueous workup. When we covered this last term, I kind of skipped the mechanism, and I said we'll cover it later. We saw the mechanism with ketones, aldehydes, and esters, but not with carboxylic acids. So let's take a look at the mechanism. The mechanism is a little bit different than the previous ones we've covered, but it's not too bad. All right, so let's say we've got a carboxylic acid and we've got lithium aluminum hydride around. A lot of students are tempted to immediately show this hydride attack in right there. However, that actually does not occur. And the reason for this is acid-base chemistry is faster than any other reaction. So in this case, what happens is this hydride, meaning this right here, is going to do acid-base chemistry almost immediately with the acidic proton coming off of the end. But that's okay. What we end up forming is our carboxylate salt, where we have that negative charge, and then we have our aluminum complex left over. So we've got AlH3. Now, if we think about this aluminum right here, it's got an empty p orbital, meaning it really wants electron density, right? So if we think about where electron density is located, the electron density is located really equally on both of these oxygens right here, right? Because that negative charge is resonance delocalized across both oxygens. Doesn't really reside on either. All right, so what we can show is a Lewis acid-base adduct where the lone pairs from one of these oxygens attacks into the empty p orbital on aluminum. At the same time that happens, a second equivalent of our hydride will attack straight in and kick up electrons. So it's a little bit weird. As you can see, it looks different from our aldehyde reaction. All right, our next intermediate, we've got this oxygen with a negative charge sticking up. We've got our new hydride that was added in, kind of sticking down right here. And we've got our prior oxygen that was over here. And actually, I'm forgetting something. This oxygen on the top is forming a Lewis acid-base adduct with aluminum, so it'd be more appropriate to actually show this as a covalent bond to our aluminum complex. At this point, this Lewis acid-base adduct portion is going to be a good leaving group. It's going to want to fall off. So in this next step, what we can do is clamp down and kick this off all in one step. All right. At this point, though, the hydride that was added in first is still on there, which means that we're stuck at an aldehyde intermediate. However, the aldehyde is actually more reactive than our starting material, so we can't stop here. It is uncontrollable. All right, so if we have excess lithium aluminum hydride around, you can imagine the next step is going to be a second equivalent of the hydride attacking in. To give us an oxygen with a negative charge. Now we've got both hydrides added in. We've reduced it twice, essentially. And then in our last step, we just need to protonate it using some sort of acid source in order to get us to our primary alcohol. At this point, there's no other reactivity that can occur, but it is important to know that you can't stop at the aldehyde. You are always going to overshoot and hit your primary alcohol. It's for that reason that we just use excess reagent. Some students will ask, well, what if we don't use excess? What if we only use one equivalent? Can we stop at the aldehyde? No. It'll still overshoot to your primary alcohol. It just means you'll have some unreacted starting material left over as well. All right, so that's a really important differentiation. However, there's another method for reducing carboxylic acids that we didn't cover. And this one's kind of neat because it gives you a variety of tools to pick from depending on the situation. So let's say we've got a generic carboxylic acid and we want to do the same reduction as before, but we don't want to use LAH. Maybe we've got other functional groups in our molecule that could react with LAH, like an aldehyde or ketone. Well, an alternate set of reagents you can use would be a borane complex, maybe borane and THF, and that will accomplish this all in one step. I did want to make a note, though, that this will only reduce carboxylic acids. Not ketones or aldehydes. Which is kind of neat. So if you want to, I should say ketones, aldehydes, or esters for that matter. So this is neat. It gives you an alternate route through which you can selectively reduce one carbonyl group over another. So for example, let's say we have this compound where we've got a carboxylic acid off of one end and a ketone off of the other end. If we treat this with our borane complex, so borane and THF, what we'll get will be a final product that still contains the ketone. The ketone will be unreacted, but then on the other side we will now have an alcohol. Alternatively, if we treated this with NaBH4 and methanol, followed by an acidic workup, what we would get is reduction of the ketone, but no reduction for our carboxylic acid. So you can see now we've got a way of targeting either this functional group, the ketone, or of targeting the carboxylic acid, depending on which reducing conditions we're selecting. All right, so pretty powerful workaround for organic syntheses. All right, there's one other reaction I did want to cover, and this is actually going way back to fall term, and that's using carboxylates as nucleophiles. All right, so let's take a look at what goes on here. So as I mentioned previously, this is just going to be our generic carboxylic acid. However, if we treat it with a base, like sodium hydroxide, we can rip off that acidic proton and get a negative charge. And sodium would be the countercation here, right? So this would be our carboxylate salt. And like I said, it's important to understand that the ate suffix indicates that the oxygen has a negative charge here. At this point, though, this oxygen is a decent nucleophile. right? It's got a negative charge. It's not a great nucleophile because that negative charge is delocalized via resonance, but if you've got an unhindered electrophile, it'll actually do SN2 chemistry. So let's take a look at the electrophiles that might work. So if we have a primary alkyl halide, like methyl bromide, this could attack in and do an SN2 reaction. And as you can imagine, when you're done with this, you could stop at something like an ester. The key thing with this, though, is that the SN2 reaction must be done with a primary or methyl alkyl halide. Doesn't work well with secondary alkyl halides because, like I said, this isn't the greatest nucleophile, it's just a decent nucleophile. So we need to have a really unhindered electrophile for this SN2 reaction to occur. This isn't a common way for making esters. In fact, I'll show you a method for making esters later that's a lot greener, but this is a valid route for making esters via an SN2 pathway. All right, so that's where we're going to stop right now. When we come back, what we'll do is we'll look at carboxylic acid derivatives, meaning functional groups that are really similar to carboxylic acids.